In this video, we're going to take a look at indices. Yeah, that's the topic. We're going to take a look at indices. Now, let's start from some stuff like when we multiply a number with itself, we have it to be written like this. This is called the second power of the number. When we have it to be like this, like 3 times, this is called the third power. So we can still continue this like that to m factors. We have it to be written like this. So this is called the mth power of a. Yeah, the mth power of a. So it means this m represents the last factor, the last number. So we have 2 here, 2 numbers, 1, 2. It's 2 here. So definitely we have m numbers here. So that's just the simple meaning. So the number that expresses this power, that is for this guy, 2 expresses its own power, 3 expresses the power of this guy, and m expresses the power of this guy. So this particular number that expresses the power is referred to as index or exponent. Yeah, the index or exponent of the number. So this word index is the singular form of the word indices. So indices means indices is the plural form. Yeah, so since index expresses the power of a number, index is also known as like the power of the number. So definitely indices means powers. So index means power, indices means powers. So yeah, so when algebraic processes of multiplication and division are carried out with different powers of the same number, that is when algebraic processes of multiplication, maybe like with between this guy now, like a squared, a to the power of 2 multiply with a to the power of 3, or we decide to divide and not to multiply, either of the two algebraic processes, we don't just do them anyhow. We don't just perform the operation anyhow. We combine them. We combine the indices, that is the powers. We combine the powers, or let's say the indices, in accordance to certain fundamental laws. Yeah, we have some laws in which we follow. We don't just combine their powers or perform operation on them anyhow. So yeah, so we have like 7 laws, or yeah, we have like 8 laws. Yeah, we have 8 laws. As you can see, we have 8 laws, and I will prove everything for you why they are like that in this video. So yeah, so in the proofs of these laws, we assume 2 things. Our assumptions. The first assumption is that we assume that m, because we'll be making use of these 2 variables as the power of a. Yeah, so we assume that m and n are positive. That's the first assumption. Then the second assumption, we assume they are positive integers. Then we also assume that m is greater than n in all, so as to make the law valid for any number or any value we put in consideration. Yeah, so we have to assume they are positive. So if a number is now later negative, it will be that number that has the negative. Because if we have something like a plus b here, if we call this a plus b the general formula for something, and we want to input 2 values, maybe a now happens to be 3 and b happens to be -2, so it means 3 plus -2. So it's the b that owns the negative. It doesn't change the formula. So that's just it. So it's, but if I say the general formula is a minus b, that affects it. Yeah, it affects it. So that's it. So let's get on with it. Yeah, let's get on with it. The first law. This is the first law we have here. A raised to the power of m multiply with a raised to the power of this. So let's see. Let's prove that. We have something like this here. A raised to the power of m multiply with this, like that. We have this. This is what we have. So this is the left hand side and the right hand side. Yeah, something like that. So this means, this expression a to the power of m means a multiplied with a multiplied with a, like that, to m factors. That's the meaning. So since we had the other time when we started, we had a to the power of 2 means a multiplied with a. Yeah, so that's it. So a to the power of m also means this. So and a to the power of n also means this. So with the multiplication sign between them. So that's it. So if we combine the two together, just as if we want to combine a to the power of 2 and a to the power of 3, we have a multiplied with a, then a multiplied with a multiplied with a. Yeah, we have 3 like this. So if we want to combine this, we have a multiplied with a multiplied with a multiplied with a multiplied with a. 1, 2, 3, 4, 5. So this guy is the second factor, and this is the third factor of this guy. So this guy happens to be the fifth factor. So it was got based on the addition of the, like in terms of position, 2 plus 3, we got 5. Yeah, so that's it. So that's how this fifth guy was got. So that is not, yeah, I'm not talking about a, adding a, I'm talking about the position, in terms of position. This is the second guy, then this is the third guy. So this guy was got based on that too. When we multiply these two guys together, we have a multiplied with a, multiplied with a, multiplied with, yeah, 2, the n plus n factors. So that's it. That's to the fifth factor, something like that. Then later we have it. So in terms of divination, we define it as this. Yeah. So definitely, yeah, instead of writing it like this, we can just say, since this is how we do get the last factor there. This is how we get the last factor. This is how we know. If we already know the last factor is 5, so we can just multiply back. We can reduce it back. 3. Then we reduce it back. Yeah. So that's the essence of knowing the first factor. So if we have a multiplied with this, we have a plus 3. And that's a to the power of 5. Yeah, you see that. So that's what we mean. So that's the first law there. So let's see the second law. Let's see the second law. The second law, actually I did not even define it, but after the proving, you see that. So it could be in this form or this form. That's the meaning. It could be in this form or this form. So we have this like this. Just the same way I've explained the multiplication one. So we have it to be a multiplied with a multiplied with a multiplied with dot 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 to the n minus n factors, to n minus n factors. Yeah, factor. Yeah, so that's just it. Same explanation. When we have, so like a multiplied with a multiplied with a over a multiplied with a. This is the second factor. This is the third factor. Yeah, so this second factor, third factor, and this third factor is got on based on saying the third factor minus the first factor. Yeah, so that's it. So get m minus, yeah, sorry, the first factor, the third factor here with the subtracted from the, sorry, the second factor subtracted from the third factor. Yeah, so that's it. So then we are left with just one factor. So that's it, like this, then like this. So we are left with just one factor. So that's it. So that's what we mean. So in terms of divination, we have something like this. We have something like this. So that's it. So let's see. The third law here. The third law we have here is this. So a to the power of m multiplied with itself n times. That's the meaning. We want to prove it's equal to this. So this a to the power of m means, sorry, this means a to the power of m like that to with itself n factor times. So that's it. So multiplying to the n factor rather. So you multiply it to the n factor means to this number of times. Yeah, so to the number of times. So then we have a to the power of m means a multiplied with l to m factors. This one also means this. Like that, we continue multiplying like that to until we get to n times. So that's it. So it means if we have 2 to the power of 3 and we have 2, we want to say 2 multiplied with like this. Yeah, sorry, just 2 times. That's the meaning. So that's the meaning. Then we now say this 2 raised to power 3 means 2 times 2 times 2 times 2 times 2 times 2. Something like this. That's what we mean. So the same thing here too. So by this we have a multiplied with a multiplied with a like that to the n factors. Yeah. So since they will multiply each other, so we have to the n factors like that. So then we have a to the power of m n. Yeah. So that's the third formula. So let's see for this now. Let's see for this. We have a to the power of 1 over m. It means a to the power of 1 over n multiply with a to the power of 1 over n like that to n factors. So when we do this, from our basic law, our formal law, first law, we have a to the power of m multiplied with a to the power of n to be a to the power of m plus n, something like that. So when we have a to the power of 1 over n multiplied with this like that, so we add the powers like that till infinity, till we don't know the number of times. So but we know the number of times, when we have 1 plus 1 plus 1 plus 1, these 4 ones, yeah, so it means 4 multiplied with 1, 4 ones. So when we have 1 over n plus 1 over n plus 1 over n like that, n times, it means 1 over n multiplied with n. That's the meaning. Yeah, n times, the number of times multiplied with just one factor. So when we do that, we get just 1. So that's a raised to the power of 1. We have just a. So this guy means a to the power of 1 over n, we have just a. So taking the root of both sides, the nth power of both sides. So we have something like this. Yeah, something like this. So this by definition, a raised to the power of 1 over n means this. So yeah. So let's see. Same thing we did in the previous when they are the same. They are kind of the same. So this the same explanation. So we have this means a to the power of m over n, then n times. Then we have it to be a to the power of m. The other time it was a to the power of 1. Now it's a to the power of m because that's m, not 1 now. Yeah, so that's it. So then when we take the n power both sides, yeah, then we have something like this. So by definition, a to the power of m over n means this. But we can also do something. From the previous, when a raised to the power of m over n means a, a to the power of m over n means a to the power of 1 over n. Then we have m. Yeah, we can do something like this. I will use 2 laws, the ones I've proven before. A to the power of m, n means a to the power of mn. Yeah, something like this. So that's what I just did. Instead of this guy is kind of on this type of form, is in this form, because this guy can also be written as m times n, and this guy can be written as m over n, can be written as m multiplied with 1 over n. So something like that. So and I brought it back to this form, as you can see. So but this guy from the previous proof we had it to be something like this. So then we'll put the m back. So this guy can be divided in 2 ways, either this way, yeah, or this way. So we can divide in 2 ways. So then we have the sixth law. The sixth law is any number raised to the power of 0 is 1. Yeah, why is this true? Let's see. Why is this true? Let's see. From the first law, a to the power of m multiplied with a to the power of n is a to the power of m plus n. So I can say let m equals 0. Let m equals 0. Then we have a to the power of 0 multiplied with a to the power of n to be a to the power of 0 plus. Let n, not m now. Let n, the number, yeah, to be 0. Then we have this, something like that. So m plus 0. Then we have a to the power of m multiplied with a to the power of 0 to be a to the power of m. So then we have a to the power of 0 because n is the number, so not m. So and not only that, we said so that's just it basically. That's just the reason. So then we divide both sides by a to the power of m. We have a to the power of 0 to be 1. So that's just it. So it's m here. We take m to be 0. So let's see. Then for the last proof that we said a to the power of 1 is this is the one but last proof. This is the one but last one. So a to the power of 3 is a multiplied with a, this, and a to the power of 2 is a multiplied with a. So definitely a to the power of 1 is a multiplied with 1, and that's a. Yeah, so that's it. So let's see for the last proof that this is the eighth proof, that a to the power of negative this means this. Is that true? Yeah, let's see. Back to our first law. This multiply with this to be this. Let's back there. So let m equals negative n. Yeah, let it be equals to negative n. So then we have it to be a to the power of negative n multiply with this. We have a to the power of negative n plus n. So that's a to the power of this. Then we have this means 0. Yeah, but from the previous proof, we already said a to the power of 0 is 1. A to the power of 0 is 1. Then we have we divide both sides by a to the power of n. A to the power of n, yeah, like this. So therefore, a to the power of negative this means 1 over this. Yeah, so that's the proof for all the laws of indices. So thanks for watching.